Hello everyone, my name is Sarish. I am a PhD student at Department of Computer Science at Columbia University, and today I am going to present a paper, Metamorphic Detection of Repackaged Malware. In this paper we present a novel technique, deceit, to address the challenge of detecting repackaged malware. Our approach is based on metamorphic testing principles, uh, automatically which automatically detects malware that leverages repackaging without needing to know the true output label of every app. Our technique does not require retraining a machine learning model, only metamorphic relation that selectively reduce feature vectors. Before we take a closer look at deceit, we must go through some background, and let's first look at repackaged malware. Repackaging refers to the core process of unpacking a software package, then repackaging it after a probable modification to the decompiled code and or to other resource files. As an example, you can imagine a malware author picking up a top app from an app store and decompiling it, modifying or injecting the library files or the code itself, and then recompiling it again and publishing it at a third-party app store. Now, two apps are considered repackaged app pair if they share at least 80% of the code and are signed by different developers. The challenge of detecting the repackaged malware comes from the shared 80% of the app structure and the code. The reason is that if malware and benign apps share more than 80% of the application code, that implies the feature representation of those apps are also very similar, and that confuses the machine learning model a lot. Now we talked about deep neural networks. Neural networks are a kind of machine learning model that relies on computational units called neurons, which are organized layers to learn patterns in the underlying data. Each layer of the network produces an output, which is used as an input to the next layer. In a classification task, a feed-forward neural network takes a feature vector as an input to train the model. And in this work, we used binary features to represent the presence or absence of components in the Android apps, such as permissions or API calls, library usage. Hence, the model learns how the existence or absence of a feature impacts each class. And ultimately, we are going to look into explainable AI. A model interpretability gives machine learning models the ability to explain or to present their behaviors in understandable terms to humans. In this work, we use LIME, which is a popular explainable AI method. The intuition behind LIME is to learn the response of the underlying interpretable model to the perturbations of the input and see how the prediction changes. We use LIME to identify features that are important for classification so that we can have a better understanding of feature distributions across malware and benign apps. We use a metamorphic relation in this work, and that is removing selected top benign features should not result in significant change in the prediction probability. You can see in the right hand side there are two plots. On the top we have the benign samples and the change in probability. In the bottom we have repackaged malware samples and the prediction probability change. The graphs are plotted after removing top 6 benign features from their feature representation, and you can see that the changes in the prediction probability for repackaged malware is significantly more as compared to the benign counterparts. And now this is the key idea behind deceit. Right? The repackaged malware exhibit many characteristics of benign apps, and by eliminating some of the top benign features, helps the model to correctly classify malware. On the right hand side, the picture depicts the decision boundary of the model in the middle, and we have the green colored dots, which are the benign apps, the blue colored dots, which are the misclassified repackaged malware, and the red dots, which are the repackaged malware which were classified correctly. Now when we remove the benign features from these apps, we can see that the blue dots convert to red, implying that they cross the decision boundary, their prediction probability changes after removal of those features, and they become correctly classified by the classifier. The deceit is a three-step process. In the first step, we train the model based on the features extracted from the apps, and once we have the neural network, we use explainable AI such as line to extract the top benign features. And once we have the feature list as well as the trained model, we can go to the third phase where we remove the top benign features from the feature representation of the apps, and then the new feature representation with the removed features becomes the input to the model, and then we look at the prediction of the model. For the experiments, we used AndroZoo dataset for training the model. We had about 2.5 million samples of benign apps and 400,000 samples of malware apps. Now, this dataset was divided into 90 to 10 ratio. 90% of the data was used for training the model, and 10% was used to tune the hyperparameters as well as extract the top benign features. For testing, we used 6,209 apps from Repackaged dataset, which were tagged by at least 10 VirusTotal scanners. And for benign apps, we randomly sampled the same number of apps from Google Play, and these apps were not tagged by any of the scanners in VirusTotal. As I mentioned before, we used line to extract the benign features. We first explain the predictions of the classifier, then extract the features indicative of benign characteristics for every prediction in the development dataset I mentioned before. We aggregate the occurrences of all these features, and that is what gives us a ranked list of top benign features. In the right hand side, we have a plot on the top which gives us the accuracy of benign and repackaged malware. The red line represents the detection accuracy of repackaged malware, and the green line represents the detection accuracy of benign apps. In the vanilla network with no features removed at all, we see the detection accuracy of malware is 87.82%. However, after removing 6 features, we see that the malware detection rate goes up to 94.56%. At the same time, we also notice that the detection rate of benign apps decreases by 1.82%. We interpret the difference as the cost of security for improved malware classification. Ultimately, we had an average accuracy of 96.17% with deceit. Our work has some limitations and threats. First of all, we use line to get the top benign features. Other alternatives exist, such as SHAP, which can perform better, and it has been shown to perform better. So it's likely that using SHAP instead of line is going to yield better results. But due to computation costs, we did not use SHAP for this work. The second, we used a simple DNN architecture with only one hidden layer. It's possible that using a different neural architecture can yield better results for deceit. And lastly, Deceit's performance is dependent on the type of features used to represent the apps. Currently, we are using only static features. Additional features extracted from dynamic analysis can improve the performance. We leave this to future work. To conclude, in this paper we present an adaptation of metamorphic testing principles to machine learning models to apply metamorphic relations to feature vector rather than the underlying information sources presented by the features. We conduct experiments on real-world repackaged malware samples, and the results show that our novel technique successfully detects malware with more than 94.56% accuracy. Going forward, we will investigate applying deceit to other learning methods such as random forest and SVM. We also plan further study deceit's effectiveness when attackers have full knowledge of the defense. Yeah, that's all for today. Thank you.
Hello, everyone. I'm really sorry that the presenter of this work has not joined the backstage room. So because the author is not here, so we cannot have a discussion. If you have any question about this work, I think you can send email to the author and asking them about the detailed questions. But here, I think we have to have a break and wait for the next presentation because the Clouder has fixed every time slot, so we cannot control by ourselves, cannot end this session in advance. So we have to have a break and until the next session comes up. Really sorry about this. And we have sent him an email and sent him a message on Clouder, but we haven't got the reply. Anyway, so let's have a break and wait for the next presentation. the Q&A session. We have sent him an email as well as a message on Clouder, but he hasn't replied. So we have no author in the live Q&A session for this paper. So therefore, we have to have a break because we cannot end. We cannot end the session in advance. I think your Clouder is working well. So I think you can find the presentation on the homepage of ICSI workshop, and you click Met, and you can find all the presentations for all the papers, and you can view the presentations by yourself, not just a live presentation.